Hello, welcome to our project presentation for the course Programming for Analytics. Me and my teammate Ramprasad will be talking about how to solve the simple assembly line balancing problem type 2 using particle swarm optimization approach. So let me walk you through what simple assembly line balancing problem is. It's basically an assembly line problem which caters to solve issues such as minimizing number of workstations, minimizing the cycle time of the process, the reduction of idle time, and workload smoothing. So there are several different types of assembly line balancing problems, as you can see on the screen right now. The one which we will be catering to is a simple assembly line balancing problem, which deals with a single model assembly. There are two types of simple assembly line balancing problems, but we will be catering to only the type 2, where the main objective of this type of problem is to minimize the cycle time for a given number of workstations. It usually occurs when redesigning an existing assembly line. So in our research paper, we had a problem, a real-life ALBP problem in an electric company located in Turkey. So one particular line, which was a single model assembly line, faced a rapid increase in demand over the last few years. So they had to come up with a new strategy to cater to this increased demand. But they had a couple of layout and location constraints due to which they cannot duplicate a line. So this ended up being a single assembly line balancing problem of type 2. So basically the problem had 18 different tasks which were supposed to be divided into seven workstations. So these are the processing times of the tasks. So the project aims to produce an optimum sequence of tasks where the tasks are divided into 7 different workstations, and the cycle time is minimized, the workload is smoothened, and the precision is kept intact. So the heuristic which we have used for this is the particle swarm optimization, which is a relatively new meta-heuristic which is based on social behavior of a flock of birds or a swarm of fish which is searching for a food in a given search space. So to understand particle swarm optimization a little better, I will take you through a YouTube video. So the blue dots represent different particles which are moving around in the search space, and the orange dot represents the best solution for that particular problem. So as you keep progressing, the red dot keeps moving around, which is the global best, keeps moving around the search space, and the other particles keep moving around the global best, trying to seek the best possible solution. Basically, a particle is nothing but a solution flying around in the search space looking for the most optimum solution. So Ramprasad will take you through the Python code of which we coded up for particle swarm optimization.
So our code starts by initializing the particles. As Sharanya mentioned about particle swarm optimization, and each particle represents a position or the solution to a problem. So in order to initialize those particles, we are calling a class. So we are defining all the attributes such as velocity, the position, and also the each dimensions, which is nothing but the task of each position has to be initialized inside the class. So the next step of the process is to initialize the position and also velocity according to an equation which I'm going to brief about in a few seconds. Then next process is to evaluate the objective functions. So one of the key things about particle swarm optimization is it is used for continuous optimization techniques, but in our case it is a discrete optimization. So we need a medium to connect, or we need a mechanism to connect this continuous variables into a discrete optimization technique. So this is where a novel method called priority based encoding kicks in. So we'll be talking about the priority based encoding in the future. So first thing is we are evaluating the objective functions of each particle by calling the function objective function. Then we are storing this position, we are storing all the information about the position and also the objective function inside the class of each particles. So first we are updating and checking the global base particle, which is supposed to at the first iteration it is nothing but the minimum of the objective value functions of the first particles. Then we are updating the velocities accordingly based on an equation, which is nothing but, so you are updating the velocity based on your personal best and also your global best. So second thing we are checking for is whether your objective function of the particle at ith iteration is less than the particle best. If it is yes, you are updating the particle's best position. If it is no, then we are just going on. If they are checking for the global best, we are checking for the global best in the second checking. So wherein again, if it is yes, then you are updating the global best value. So now let me go through the inputs and also the outputs of our program. So now the input is basically nothing but the task and the number of workstations and a DAG. A DAG is nothing but a directed acyclic graph. The directed acyclic graph contains information about the precedence, which process has to come before what, and also it follows a precedence technique. The DAG has V task with E nodes, E edges of the list. So the output is nothing but it goes through this particle swarm optimization and gives you a minimized cycle time, allotment of task, and also the objective function. As you can see that initially all the particles are assigned as shown in this equation 1. So here each particle has its own dimensions. So these dimensions are nothing but individual tasks. So each particle will have 18 dimensions. So we are initializing each of these 18 dimensions according to this equation 1, and also we are initializing this according to the velocity of 0. So when I was talking about the priority based encoding, I kind of mentioned about the relationship between discrete and also the continuous variables. So this is where our priority based encoding program comes in. So this process takes in DAG and also the priority is nothing but randomly generated number between 1 to 0 for each of the particles and generate a sequence accordingly. So for example, let me go through the precedence diagram which is shown here. So it is very easy to see the diagram. So from the diagram you can see that the independent tasks are 1, and then so it is removed and then and it is updated into a list. Again when it comes to 2 and 3, so 2 and 3 becomes independent of the next iterations, and then 2 and 3 gets iterated to the next list. So now here, based on this priority between 2 and 3, whichever has the highest priority will get updated first. So accordingly this procedure gets repeated and then the sequence is shown as below. So after running our particle swarm optimization, we came to a conclusion that the theoretical cycle time of 103 would be the best. And also we are updating the velocity according to the equation of 4 and also equation 5. See, these are all the results which was produced from, these are the results produced from PSO. Now you can see that initially all the particles are distributed randomly across the search space, but as the solution got converged, every particle got aligned between this 103. So this is nothing but our solution worked, and also this can be validated against a paper. The paper had 103 cycle time, and we also got 103, and this is the workstations which was allotted for different tasks. And this is our project. Thank you so much.